On March 23, 1989, the Journal of Electroanalytical Chemistry published the article entitled Electrochemically Induced Nuclear Fusion of Deuterium. The authors are Martin Fleischmann, professor of electrochemistry at the University of Southampton, and Stanley Pons, professor of electrochemistry at the University of Salt Lake City. The history of cold fusion begins from that date. The authors state that they obtain a quantity of thermal energy much greater than that introduced with the electrolysis of heavy water, and that this excess cannot be justified by any chemical process. Their idea starts from three fundamental elements. First, the cathode is palladium. 2. Electrochemical reduction of deuterium involves the absorption of a deuterium atom into the palladium lattice. Third, the deuterium atom in palladium behaves like a charged species. The Fleischmann and Pons experiment foundations. The left image is the original device presented by Fleischmann and Pons. It is a calorimeter that also functions as an electrolysis cell. The temperature of the electrolyte at a given input power compared to the calibration curve at the same power determines the extent of any excess. It is a power balance. The output power must consider not only the thermal power generated by the electrolysis, but also the contributions of the heat removed toward the outside. From the gases generated by electrolysis, from the steam of heavy water, and from the heat transmitted by radiation to the outside. These contributions can all be evaluated with great accuracy. The Fleischmann experiment access heat measurements. By way of example, the calibration curve of a calorimeter similar to the one shown previously is given, which show the unique dependence of the temperature on the power input from the internal heater. In that calorimeter, electrolysis is now running with the generated thermal power P input, and the observed temperature is higher than that expected from the calibration curve. This implies that a process is taking place in the calorimeter to which the calibration curve corresponds to a higher input power. The excess power then is given, as shown, by the difference of the two values. The Fleischmann-Pons experiment. Wide palladium cathodes. The Palladium-hydrogen system is well known for forming solid solution with hydrogen and its isotopes. It's shown that at room temperature and atmospheric pressure, 8.85 cubic centimeter of palladium, corresponding to 106.4 grams, absorb a volume of hydrogen in the atomic state which is 994 times greater. The system of hydrogen absorption isotherms as a function of the ratio of hydrogen atoms to palladium atoms shows three phase regions. Alpha phase at values close to zero of the hydrogen-palladium ratio. Biphasic system consists of alpha plus beta over a wide range of the palladium-hydrogen ratio. As the hydrogen pressure increases and the temperature decreases, one exits the biphasic domain where only the beta phase exists. The adsorption of hydrogen into palladium is due to migration into the interstitial sites of the cubic phase-centered lattice of palladium. Two types of sites are occupied as a function of the hydrogen-palladium ratio. Octahedron size 1 per cell, constituting the alpha phase, and the thetaedral side 8 per cell, which make up the beta phase. The Fleischmann and Pons experiment. Why the palladium cathode? The first two cathodic reactions compete in the formation of adsorbed deuterium. The absorption process is favored by the increase in the surface activity of deuterium and by the diffusion rate of deuterium in the palladium lattice. The accumulation of deuterium on the surface favors the desorption of deuterium as a deuterium gas. The level of confinement of deuterium in palladium depends on several factors that are not easily controllable. In general, they are influenced by the chemical purity of electrolyte solution and the impurities present in the palladium that should be less than 10 parts per billion. Further, reduced palladium structural imperfections, cleaning of surfaces and their catalytic activation to increase the specific surface area, conduction of electrolysis by choosing the optimal current density is just an empirical way. The Fleischmann and Pons experiment. Why the palladium cathode? It was known since 1929 as the Kuhn effect that palladium, in the presence of hydrogen, does not behave as a pure electronic conductor, as expected for a metal, but presents mixed conduction because it's a conductor for hydrogen ions. The consideration reported in the article by Fleischmann and Pons is highlighted here, in which the proton state of hydrogen inside palladium and its mobility given by the high value of the diffusion coefficient are underlined. This state is unique in cases of a metal-hydrogen interaction. For comparison, the diffusion coefficients of the proton at 25 degrees C in liquid water and that of the hydrogen atom in iron in the solid state are reported. The difference in order of magnitude illustrates the peculiarity of the hydrogen-palladium system. The excess heat. The most significant evidence of the experiments performed over the years on the model of those of Fleischmann and Pons is that the excess power measured increases as a function of the deuterium-palladium ratio in the cathodes of the various electrolysis cells tested. The data are substantially connected in a curve that grows almost exponentially. It should be noted that the graph shows thousands of experimental data obtained in different laboratories around the world, not always obtained following the same experimental methods as Fleischmann and Pons. Note that the curve has further enriched with consistent data over the years. Why still skepticism? The vexed question about cold fusion was and still is, given that no physical and chemical phenomena can and do not be responsible, what is the nature of excess thermal power? The presence of deuterium nuclei made one thing from the beginning of nuclear fusion reactions as occur in the vacuum between high-energy particles and in the stars at very high temperatures. In particular, the reactions considered were the following. Numerous experiments, such as Fleischmann and Pons, report the almost always non-reproducible presence of either tritium or neutrons or helium-4, but in no case does the number of particles detected justify the excess power measured in the same experiment. This aspect, as well as the difficulty of reproducing results, constitute the sore point of cold fusion. All this in the absence of any established theory. The theory that seems or seemed more convincing, but still not fully developed, unfortunately due to the premature death of the author in 2000, is that of the theoretical physicist Giuliano Preparata. The theory explains, on the basis of a quantum electrodynamics, which describes all the phenomena involving charged particles interacting by means of the electromagnetic field, the possibility that in the condensed matter two deuterium nuclei can interact by overcoming the Coulomb barrier. Formation of a highly excited helium-4 nucleus, which releases its energy to the lattice mainly in the form of heat, in a time less than its lifetime, which is about 10 to the minus 21 seconds. According to the theory, this is possible in the presence of a coherent plasma made up of deuterium ions and electrons of the electronic structure of a palladium. The theory also explains the presence of a threshold in the value of the deuterium-palladium ratio and the existence of the gamma phase. The appearance of this phase would be justified by the decreasing trend of the relative electric resistance of palladium when the deuterium-palladium ratio tends to 1. The palladium-deuterium or palladium-hydrogen system does not behave like a pure electronic conductor, but has an ionic component, as we have already seen. The presence of these ionic components is responsible for the growing part of the graph.